it's great to have Fahad with us. Actually, Fahad was introduced to us by Vaishak, and he had visited the lab a few months ago. He is a neuroscientist at the Cognitive Brain Dynamics Lab as part of the National Brain Research Center in Gurgaon. He is working, I think, currently at the intersection of neuroscience and human experience, and how people react to content, I think specifically videos. And it's great to have Fahad here give us a talk on this topic, and very excited to see how his research can intersect with some of the things that we are doing in the lab, and also aid that research. Over to you, Fahad.
Thank you for the warm introduction, Vivek. And thank you, MSR, for giving me this opportunity and having me. So, the paradox of experience. Now, what do I mean by that? So, during one of his famous performances, Charlie Chaplin once told a joke, a good joke. The crowd erupted in laughter. He then proceeded to repeat the same joke. Some of them laughed, most just smiled. When he said it once more, people started to become restless with boos and murmurs. Now, why is that? The same stimuli from the same source gave opposing experience in them, and in turn us too in similar contexts. Experience is something that is hard to define and harder to measure. 50 years ago, we had things like this to measure the most aired TV shows in US and UK. Then we invented the Nielsen ratings, and 20 years ago, we first started measuring clicks online and now tabs to find patterns and predict what might happen given the past data. But generating countless patterns is not the problem right now. It's to choose which is the right one. And neuroscience can not only guide us, but inform us as to why this happened. So to go back to the example, it's not in the joke itself the answer lies, but in ourselves. So to understand experience is to understand ourselves. And understanding ourselves begins by understanding our brains. If you search on Google how the brain works, you'll find countless blogs and videos on left brain, right brain hypotheses, the reptilian brain, mammalian brain hypothesis, etc. Whilst these are in and of itself not entirely wrong, they're 40, 50-year-old theories, and it really doesn't tell you fundamentally how the brain works, and more importantly, why the brain is organized in such a way it is. On the other hand, if one is to search on how AI works, they'll be met with detailed state-of-the-art information regarding this. Crazy, isn't it? So let us begin by filling this gap in our understanding of the brain. To start off, there are many levels to understand this, from the molecular levels of proteins and mRNA networks, synaptic levels, right up to single neuron level recordings, then circuits of neurons in cortical columns and neuronal networks. And finally, the systems level and whole brain networks. This will be the level we'll be interested in. Specifically, the cognitive and computational aspects of it. Cognitive pertaining as to what is happening in a person's mind that gave rise to their behavior, and computational as to what computations are happening under the surface that led to that. Now, I'll begin by giving you a metaphor to keep in mind when thinking about the brain. It's the brain as a scientist. Now, the question you all be thinking would be, why not a computer? Not. After all, that is the most famous metaphor for the brain, right? The brain as a computer. The reason is that the brain does not have access to reality. It has no direct access to the world, and it has to infer, or rather reverse infer, the causes of events happening in reality. Now, how does it do it? It does in two ways. The first path is by sensors or sensory organs. Now, one way to describe sensors are as devices that co-vary causally with a specific parameter in the environment. In vision and visual system, the parameter is 400 to 900 nanometer, or the visible spectrum in the electromagnetic spectrum, or as well as hearing or the auditory pathway, where the parameter ranges between 0 to 120 decibels, as well as olfaction, taste, which depends on the chemical properties. As well as the external receptors, we have internal receptors as well, like baroreceptors for inferring the pressure in your blood vessels, proprioceptors present in muscles and joints for inferring the position of body at a certain time. Now, these sensory channels bring in and process information, but that is not the whole of it as to what we all think. There's another side to this coin. As any good scientist would do, it creates its own hypothesis. Now, these hypotheses are then tested out with the data brought from the real world through the aforementioned sensory channel. Now, this second path are the predictions. In other words, the brain is an inference engine. It does not just sit there and passively process information brought in by the senses. It rather actively generates its own reality. It actively generates the predictions, tests them out with the reality, and then the actual perception occurs. There's two directions of informational message passing schemes in the brain. One is the top-down predictions and hypothesis, which is the blue arrow, and the other, the bottom-up reality or sensation, the red one. Not only this mechanism helps us in having an advantage in terms of survival, but it allows the brain to extract the statistical properties of the environment and transfer that to other areas. An intuitive way to think about this is thinking them as probability distributions. Suppose imagine yourself in your backyard, in your home backyard at night, and you heard a growl. The maximum probability you can assign that in your predictions can be to your own dog, and maybe with a less probability to the neighbor's dog, and absolutely no chance it can be a wolf. Now, flipping the script, imagine you find yourself in a jungle at night during your yearly vacation of work. A growl here would undisputedly be coming from a wolf and not the dogs, and you need to run away fast. We'll come back to predictions in a bit. Now, the next property of the brain. Most of our school and college days, we learned the brain is stuff made up of billions of neurons and trillions of connections between them, and there are a few lobes that do certain functions, and that's it. Reality is, however, much more nuanced and complicated than that. Now, to understand this, we need to see it as a modular or a segregated and interacting network of subsystems. Division of labor is prevalent in such complex systems as most of you can imagine. I'll explain this interesting concept in the light of vision, since visual cortex is probably the most famous, most studied, and most understood of all brain areas. Now, if you look in the visual cortex, there are patchy subdivisions into V1, V2, V3, etc. until V5. So it's not a full cortex in and of itself. It has subdivisions to it. So yeah, most of our school days, we learned that the brain is a stuff made up of billions of neurons and trillions of connections between them. And there's a few lobes that do certain functions, and that's the end of it. But the reality is it's much more deeply complicated than that. To understand this, we need to see it as a modular or segregated and interacting complex network of subsystems. And division of labor is prevalent in such systems, as most of you can imagine. I'll explain this interesting way the brain deploys this in the light of vision, since the visual cortex is the most famous and most studied and most understood of all brain areas. Now, within the cortex, there are subdivisions of patchy cortices into V1, V2, V3, all etc., all the way until V5. Now, when you're watching some real life event unfold, you're not processing it all together the same way. Instead, you'll be processing the form, the color, the depth, the motion, all in separate interacting subsystems, giving rise to your final perception. In other words, the neurons that processing them are different as well. This actually came from the pioneering work of Hubel and Wiesel in 1950s, for which they eventually earned the Nobel Prize. They measured the neural recordings from a cat, which is anesthetized from neck below, as you can see in the top left slide, and electrodes were fitted onto the visual cortex, and they put light bars in front of a screen and watched the neurons fire. The right is a picture of only when one eye is forced to see that, the other eye is masked. Now I'll play the video, the famous video. You will hear some neurons firing when the light is in a specific orientation, but not to any other orientation. Headphones are recommended. Now they don't fire. So what we saw is a specific division of labor present in the visual cortex with respect to orientation. In other words, the neurons that fire for this specific orientation fires only for this and not to anything else. And this same concept applies to other variables in the vision processing as we mentioned as well. So in a nutshell, when you're seeing a moving car, certain parts would be into the object recognition, say the tires, other parts would be the color of the car, other parts would be the motion itself, and that stitches together the final perception you'll have. Now, if some of you are thinking that this works awfully similar to a deep convolutional network, then you're absolutely right. There's a recent evidence that's mounting towards this view of human object recognition is very similar to the deep convolutional neural network. The gamma band here is a frequency band in the EEG. Now, coming back to the predictions, if there is no difference between the predicted causes and the actual causes, it's all well and good. But like most things in life, there are often differences. This difference, termed prediction error, is the main currency used by the brain. It denotes how strong your predictions were and how surprising your environment is and how learning should be. When such errors do occur, two things can happen: inference and learning. At this point, it's somewhat useful to explain the difference between the two. Inference here is mainly related to the perception in the sense of inferring possible causes of events, while learning here is parameter estimation in a machine learning sense. Inference can be changed in two ways. Now, let's go back to our example of the backyard. Suppose you hear a growl and you look and you see a faint silhouette of something that resembles a wolf. You can do a perceptual inference by updating your priors that it is indeed a wolf. It is a huge error because a wolf is not supposed to be there. It's either dog or some bigger dog, and that's it. Having a wolf is a huge error to your previous predictions. So you update your priors that a wolf can be there as well. The other way is you'd actively go near and confirm it really is a wolf and not a huge dog. In other words, you actively sample the environment, maybe going towards it, maybe adjusting your vision and make sure that the eyes are not playing on you. And this is active inference. These are the two main forms of inference. Now, learning. How does learning occur in the brain? It is mainly associative in nature. The Hebb's postulate in 1949 is a very intuitive framework to understand this. Hebbian learning postulates that neurons that fire together wire together, and the corollary being neurons that are out of sync fails to link. Suppose you are doing a task as shown, and there will be some task relevant neurons in the network encoding this that would fire together. In this case, the red neurons, and to give an illustrative purposes, and they would speak with themselves far more than with the task to relevant neurons, which is the black one. Doing this repeatedly strengthens the association strength between the red neurons again and again, as well as weakening the strength, the synaptic strength between the task relevant and task irrelevant neurons. This strengthening of the associative connections between them and eventually leading towards synaptogenesis is learning. Certain areas of the brain, like the striatum, the hippocampus, the prefrontal cortex, contribute heavily in such associative learning mechanisms. It can be spatial, like you would know how your chair, table, laptop are all organized given your office effortlessly. You also know the sound of the doorbell after you order your food from Zomato, and that is coming from the delivery guy, which is association in time. Now, reinforcement learning is a famous type of this associative learning in reward learning. Here, the prediction errors or reward prediction errors are the main currency used. It owes itself to its primal form of classical conditioning by Ivan Pavlov in 1920s, for which he also won the Nobel Prize. It can be summarized as this. Suppose there's a dog and you ring a bell, which is a neutral stimulus, neutral meaning it has absolutely no value to the dog. And if you give it food, it would salivate. Now, these are two separate events in and of itself. During the conditioning, you ring the bell, and immediately afterwards, you give the food to the dog. In other words, you are pairing both of them. And the associative memory learning kicks in. And afterwards, after the conditioning, just by ringing the bell, the dog kind of predicts that food is coming and it shows salivations or behavioral change. Now, in this case, the dog is a passive actor, as in it's not actively going and doing anything to learn. The other active version is the operant conditioning by P.F. Skinner, Watson, etc. So a good example to do that, suppose you find yourself in China, hopefully not these days, and you go to a food and drink dispensing machine, and there are 4 buttons, red, green, yellow, and blue. And each of them, if you press, would give you a certain food. You don't, it's written in Chinese, so there's no way for you to understand what it gives. And all you know that is you really, really want a can of Diet Pepsi and fried chicken. So you press the green button and you have a very low prediction it would give out what you thought it would give. And to your pleasant surprise, it actually gave you Pepsi and fried chicken. So that if you zoom out and in the prediction error scheme, if you look into it, you have an expected reward prediction that okay, if I press this, there might be 10 to 20% chance I would get. And the actual reality actually gave you. So the difference between the expected reality and the actual reality, there is an error. In this case, it's positive because the value is something that is needed for you. So it's a positive reinforcement learning. And as you repeat this every day, you get accustomed towards it, and the associative learning and the strength gets more strengthened. And suppose in a couple of weeks, you come back again and press the green button, and to your horror, you get something like a green tea and dumplings, which you didn't want then. What happens then? Now you are expecting that you would be getting what you were getting with 90 to 100% confidence, and you got something you least expected. And not only that, the value is something that you don't want. This is negative reinforcement learning. So this associated learning is mediated by reward prediction error, which are stamped onto the brain by the neurochemical dopamine. And this in many ways gave rise to the reinforcement learning algorithm used in machine learning. The objective function in both cases being minimizing the error and maximizing the reward. And in some ways, the learning rule implemented are not too different, the temporal difference algorithm. Here, an agent maximizes the reward by selecting some action policies and repeating that again. So this again drives home the notion the underlying computational principles used by the brain and machine learning algorithms are all not too different. A recent advancement even proposed the existence of a meta-reinforcement learning in the brain, whereby the prefrontal cortex creates an emergent algorithm. Or to say more specifically, the striatum or deep brain areas teaches and trains the prefrontal cortex to create a second algorithm from a previously existing reinforcement learning algorithm. Now, this second algorithm is much more efficient in gaining the same value given the behavioral policies executed and sensory states experienced. Now, hierarchical organization is a key property in the brain. From processing lower level like unisensory perception, multisensory integration, sensory motor mapping, to higher levels like context processing, decisions and rewards, outcomes and value, it is all pervasive through the brain. So as you go up the hierarchies, the topographies of each expand. For example, topographies for processing spatial information are known as spatial receptive fields. And as you go up the hierarchies, the field increases. Same way, in the time domain or temporal information, there are temporal receptive windows, which again increases as you go up the hierarchy. One easy way to imagine this is to see yourself One easy way to imagine this is to see yourself in a tower and there's a battle going on outside. From the ground floor, looking outside seems very chaotic, ever changing. But as you go to the top and the topmost level, when you reach in the hierarchy, things suddenly start to make more sense and are less chaotic. The question as to what specific kind of hierarchy the brain employs, as in, is it a hierarchy of sequence or a hierarchy of projection of fibers or for progression of scales, we don't have 100% evidence. But for all we know, it could be a mixture of all. So to recap, and a picture is like 1,000 words. This can very well recap all that we learned about the brain right now. At every level, if you look down, at every level, there is a competition between the bottom-up sensation and top-down predictions. The E here represents expectations and R reality. That is all. E as in predictions, R as in the sensations coming up. And the winning one goes up the hierarchy through the functionally segregated networks that underpins them, creating the associative learning while they go. So what's the ultimate? So what's the ultimate point of all this? Why is the brain doing this? Although we don't have a definite answer to this, a very desirable answer comes in the form of minimizing the prediction errors, which I mentioned earlier. In other words, the brain is in the business of accurate modeling of the world. And this is done by trying to minimize the difference between expected reality and the actual reality. Finally, with any hierarchical structure, Bayesian analysis becomes a natural way of inference. So in terms of being a Bayesian, one can say that the brain is actively trying to minimize the difference between the priors or predictions and the likelihood or sensation, or maximizing model evidence. In terms of machine learning, it can be cast as minimizing the cost function through variational methods. And in terms of information theory, it can be cast as minimizing the self-information or surprise associated with it. Whichever way we look at it, predictions and prediction errors are an inescapable fact of existence. And this is because we live in a constantly changing world. They're also the reason we are able to learn, experience, act, and survive in the world. This concludes our part of understanding the brain. We'll be focusing on the research and the practical applications. So if anyone has any questions regarding until this, now's the best time to ask. Okay, no questions. So we go through the research that we are doing there. So my main research includes understanding the memory and learning in context of prediction errors. I use naturalistic videos or movies primarily because most of the memory literature in neuroscience uses stimulus like words, faces, images, etc. as stimuli, and they
Fahad,
make people
sorry to interrupt.
yeah,
I think there
sure,
is a
sure,
question from Vishesh. Vishesh, do you want to go in?
sure,
Yeah.
sure.
Yeah, actually, I had one or two questions. Sorry, I could not connect earlier. Yeah, so my one question was that earlier you had mentioned that the neurons which are connected for a particular task will get their connection stronger and stronger with when they fire together. But how do
Yes.
you even begin to know which neurons are selected for that specific task?
Right. So the question is a good question. The question is, how do you know which neurons are pre-selected for that specific task? No, it can be rephrased in the sense that suppose if I'm watching a car move, there would be certain neurons encoding the color of the car, certain neurons encoding the motion of the car. So these neurons would be already processing that. Even the first time I'm processing that car. Second time, if I'm watching the car again, the same neurons would fire the same way, assuming the stimulus didn't change. So that's how the selection happens. It already gets fired when you
Uh,
first watch the stimuli.
Okay, I mean, it was more towards that. Suppose some neurons are linked to the optic nerve initially, and then they will initially be processing the image from the eye. But the neurons which are connected further down the line, you do not know. Like they would have come from multiple different areas. Some would have come from the ears
Right,
as well,
right,
and things like
right,
that. So,
right.
okay,
So
so
that's
you're
where the
saying that.
hierarchy comes into play. Yeah, good question.
Mhm.
Like
Yeah,
that's where the hierarchy
right.
comes into play. So as you go up and up the hierarchy, the complexity increases exponentially. In one sense, maybe you just want to see the car and appreciate its color, And that comes from the higher level thinking or higher level cognitive process in the hierarchy. And the visual processing remains the same. In other words, there's much more depth in as you go up the hierarchy than lower. And they change as well. And even if you're watching the same car again, and this time if you appreciate the motion of it, it might be so that the lower level hierarchy neurons or the visual neurons encoding motion would be the same regardless, but the upper level in the hierarchy would change.
Okay, right, got you. And the other question was how interpretable the brain's learning is, in the sense that you were talking about Bayesian, it is somewhat close to Bayesian learning on priors and prediction. But how do you even understand how the brain is representing its predictions? Because they would just be a neural activation map, right? So,
Right.
how do you interpret that information, that what it is representing?
Right, good question. So there's like three ways to look into it. One is animal recordings and direct recordings from neurons. And in this case, I'll say about animals, suppose there's some mice who is conditioned to go to a path A to path B. And when it goes to path B, there will be a reward. And there are dopamine neurons in the brain that encodes the expectation of there's a reward coming and the actual reward itself. Now, when you give a reward at B, these neurons fire in a certain way. But when you take out the reward, as in you stop giving the food even after it traverses the path from path A to path B, there is a specific activation that denotes that absence of reward. In other words, and if you look into the synaptic connections, after a while, it decreases. This can be done by optogenetics methods and other recordings, but there is mounting evidence that in the last 40 years that showed that the synaptic connection strength decreases. And second way is behaviorally, you would see some changes. Like the rat would be less approachable to do that goal, or it would be more aversive. Now, if you replace that food with something else like a foot shock or some bright light that is very harmful or something, the rat would completely change the outcome. As in, this is now a like avoidance task. It's not at all valuable to that. So it would learn not to do that. So direct recordings and behavior, that's how we know that the brain represents prediction. And when the predictions are not met, it changes it synaptically as well as the effect reflecting behaviorally. The same thing happens in human neuroscience studies when you image them under a scanner as well as EEG and behavioral studies. I am actually showing one right now, so that might give you an answer in a better sense as well.
Okay, cool. Thank you.
All right. So thank you for the question too. So I use naturalistic videos or movies because most of our memory, most of our experiences in the real life is close to that. And most memory literature uses stimulus like images, words, faces as stimuli to make people remember and later recall the memory performance. Now, I'm of the opinion that the closer we get to real life scenarios like this, the more precise our understanding of the brain would be. And videos are the closest replica of the real life experiences. Now, Alex, I'll go through my experiment design and results. Obviously, I'm oversimplifying here. There's more to this. So on day one, people would be watching a video. This is a certain small context of the video. Each scene would be 7 seconds with 1 second blank screen in between. This is also known as prior formation, that I introduce this as a prior for them. Why? Because next day they'll be watching the same movie again, but there's a difference this time. So if you can see my cursor, the original way they watched the movie was this one, the shaded red areas. That's how they originally watched. The second time, if they watch, they'd be predicting after this would be coming, and after this would be coming. So they're already predicting after this next scene would be like this. But instead, I won't show that. I substitute that with another scene that is relevant to the context, but the content would be completely different. Now that introduces a prediction error there. Between this memory of scene and this memory of scene, the sequence gets changed. How it changed is the question of the study, but we know that they'll be predicting this and the prediction error happens here. Now, a later day, their memory strength of these scenes are tested. Here's some interesting results. The memory of the new events. So here the blue one denotes the memory of the new prediction error memories, and the yellow one denotes this one, the start to pre. This is the control sequence. Control precisely because the first and second day they're watching, this won't change. The first two scenes won't change, and they are seeing or experiencing this consecutively the same exact way. Now, interestingly, there is no difference between these two memory strings. In other words, the prediction error memory reached one shot learning. One shot learning because it only took one shot to attain the same memory performance as the control one, which required two or multiple experiences to get the same result. And the caveat is you don't need to experience something multiple times or repetitive learning. In other words, you can just have a prediction error induced and the memory updates. And what about the old memory strand that we substituted with the new one? It just so happens that the old memory strand considerably weakens in accuracy, and this is the reaction time, how easy for people to respond to that. So it is much faster for them to elicit this is the memory sequence compared to the older one. We also included a neurocomputational model to understand why this is happening. The implications of this research is in education and learning, not only in children, but in us adults as well. Current days, the focus is more on acquiring more and more information, i.e. repetitive rote learning, whereas the more effective learning is in updating the old information, because that's what true learning is, updating your older priors with newer ones. Another research that I'm part of is with Gargi, who is also here with us today in the meeting. So what we've done is understanding how negative emotions are processed and how that changes with age. It is well-known neuroscience literature that as we age, as we go like 40, 50, 60, 70, 80, and so on, our ability to process negative emotions like anger, fear, etc. gets affected. In other words, we get less sensitive to them. So in our experiment, we had people watching from both age groups, young age group and older age group, watching a famous suspense movie. So we chose this movie because this is a widely used movie by other research groups as well. It is a standard in the literature. So that gave us that. And we chose suspense because one, suspense has never been done before. It's mainly fear and anger that's been done as negative. Suspense is something that has been never been done, and it's a very gripping negative emotion. And another unique thing about suspense is that you can never simulate suspense. You can simulate a sadness by remembering an old event or simulating fictitious future events, happiness, anger, even fear. But suspense is something that you cannot simulate. Now, while they were watching scanner, we scanned the brain and got the brain dynamics. So these are their fMRI results. So fMRI is an indirect measure of neuronal activation. So it's not electrical recordings as in EEG or direct electrode implants. This is through their hemodynamic activity, or how the blood oxygen consumption rates of neurons change. So when they're firing, the neurons need the blood through which the oxygen diffuses into the neurons. And more the neuron needs to be fired or activated, more blood would be consumed by that. That is the basic idea of an fMRI. So this is the fMRI brain scan images. What you see on the left is the younger people comprising of age 19 to 35. And the right is the older age group, 65 to 80. Clearly, you can see the brain dynamic and brain areas underneath processing suspense changes. And this is specific to only processing suspense. Now, the movie would have different scenes. Some would have high suspense, some would have like no suspense at all. That is the control conditions for us. And we validated that experience with another sample of the people to validate that our approach. And as you can see, this is just for the suspense, the same areas that processing suspense, the activations widely differs in between age groups. Now, this is the bold activation, which is the blood oxygen level, how much of that is activated on an area known as the prefrontal cortex, the front part of your brain. The upper segment is the young people, and the lower is the older people. The shaded part just represents the control areas, but you can disregard that. Now, as you can see, there's a huge difference between the younger people and older people in terms of how much blood that their neurons require. Now, this is another part, amygdala. Most of you would be familiar with this area. This is an area very famous for processing negative emotions and the value associated with that. Again, the difference is stark in young and old. We have other key areas as well in deep brain structures, but for the interest of time and brevity, I'm not showing that. So this work has the potential to be translated to real world benefits like understanding differential negative emotion processing, and not just among normal people, but in people having mental health problems as well, say schizophrenia, depression, anxiety, how those people perceive negative emotions differently. Are they overrepresenting it, or are they underrepresenting the actions that need to take, etc., etc. Now, we have developed a startup around the work that we have done. It's mainly focused on videos for a long time. So our startup can be summed up in two sentences. One, measure experience from the brain, and second, augment your creations using this. Now, creations here mean the things that we make for experience, like movies that we watch, ads that we are forced to watch, product or tutorial videos, software design, which we all use and in the days of our life. And all of this comes under the umbrella term of experience. Our approach differs in other ways by we combining cognitive neuroscience and behavioral design, and we combine that with computational modeling and electrophysiology, in this case EEG, and we combine that with state-of-the-art machine learning tools, which give insight into the experience, which is visualized, and the next step is predict how the real-world impact is going to be. For instance, how much views can my video generate even before launching it? So if you can understand the insights of that even before launching and make it better and estimate how much views can expect, that is a whole new field itself. Same can be done on movies as well, like how much box office can I generate in the first 2 weeks, given the trailer, given the movie, etc. I'll give an example on that. Sample study. So this is a video that we tested on, and the video would be played in the top, and the bottom is experience, or in this case, engagement, emotionally laden engagement. It evolves in a graph. I'll play that shortly. In the graph, there'll be a red vertical line going horizontally, depicting each time point in the video and how the engagement evolves. The higher values in the graph at particular points refer to higher engagement. Headphones are a really recommended thing in this as well.
Now you know how it feels to get motor neurone disease. Help us fight back.
Okay, now this can be applied to any genre of videos, like educational videos, to know how people's engagement is going on about, or say a new product launch or product videos and see how the community accepts that. Now, this exact same framework can be theoretically applied to software interaction as well. But it becomes more harder because software is a two-way interaction between a human and a computer rather than a passive one-way interaction like watching a movie or video. But the kind of insights that one can gain, I'll show that. So we compared this in the light of cognitive load and ease of information processing in team collaborative apps, which is all the rage nowadays. And the softwares that we analyzed was Microsoft Teams, Slack, and Zoho Connect, two other workplace collaboration apps. The goals we analyzed, because that's why we use the apps in the first place, right? To as a means to a goal. The goals we analyzed were inviting a friend and scheduling a meeting. We chose this mainly because they're fairly frequent goals to be met by people using this software. And instead of choosing experienced people who has prior experience of using this or are using this frequently or daily, weekly, we chose naive people, as in people who have absolutely no experience with this, have never used an app, these apps, or even a related app in their life. There's a good real world reason for that as well. There's a lot of small and medium business owners, medium business owners that will be forced to resort to such collaborative apps, if not already, because of the ongoing pandemic crisis. Hence, it is easier and more effective to test on such people because that's where the adoption comes from. The tech community would adopt it regardless. Those are the people where it needs to be penetrated more. So what you see here is how learning occurs. So the y-axis is the learning duration for, in this case, the goal is creating a meeting and the learning duration is in minutes. It's Slack and Teams in the middle and Zoho on the right. The three color represents the different trials of learning. As the first time, how long did they take? Second time when they do the same goal with different contexts, how long did they take? And then the third time. And as you can see, Slack takes extraordinarily large amount of time compared to the other two. And Teams had a much smaller learning curve or duration. And it's interesting, it's not that surprising to see all of them decreases because people learn eventually, but it reaches an asymptote, or at least in this final trial, and the asymptote massively differs between Slack and Teams. However, when you add the goal of inviting a friend, the whole thing switches. Slack had a much better performance than Microsoft Teams as well as Soho. Now, this is just the behavioral results. We want to know why this happens, like what's the neural basis of that. So we used a hierarchical neural computational model on this to know why this happens. So the parameter on the x-axis here is the information accumulation rate. In one sense, you can see it as the cognitive ease in processing. Like suppose in a human computer interface light, you can see how easy it is for a human agent to understand the interface and process it. Like the more it is, the higher it is, the better. The faster you can accumulate information without needing to generate by your own. Like as in, you don't have to input so much cognitive control and effort into it. So the deep purple here is the Slack, the light purple here, violet here is the Teams. And in the inviting a friend, Teams, the mean maximum probability is on 1, and here it's just below 4. And Slack significantly outperforms Teams on this goal. And in the other goal, which is creating a meeting, Teams has significantly better information accumulation speed compared to Slack. Now, even within the same participants that did that, we can see it was much more easier for them to create a meeting compared to inviting a friend. The right one here is creating a meeting, and the left one is inviting a friend. The y-axis all shows denotes the posterior probability as well. So this gives you a glimpse of the kind of insights that you can get when you combine neuroscience with the already ongoing machine learning and other behavioral analytic techniques. And there's other levels, deeper levels that I can't show because of the interest of time and explanatory power as well. That when you do more deeper analysis in EEG, like how often do they need to recall their past memories or how much attention they have to pay, so and so. So the goal is to work with product teams or design teams, and the kind of insight they would get while access to these kind of information is potentially huge. Now that wraps up our talk. And to conclude, I would love to end with a quote I heard a long time ago, but didn't quite get the deep grasp of it then. But now I think that code represent what we are doing more than anything else. It's by Steve Jobs, and it's you got to start with the customer experience and work backwards to the technology. Thank you, everyone.
Thanks, Fahad.
You.
So yeah, Monojit has a question. So go on, Monojit.
Yeah, so Fahad, this is
Yeah.
like really fascinating, very interesting.
Thank you.
Yeah, so I was wondering, the video example that you gave,
Hmm.
so what you are essentially measuring is sort of the initial shock value when someone, or the emotional, reaction when someone
Hmm.
watches that video first time.
Hmm.
But of
Hmm.
course, you started with the Charlie Chaplin example, right? Where the
Hmm.
same example repeated multiple times, the effect
Hmm.
will die down.
Yeah.
And what makes something viral in the short run might be to some extent associated with what you are measuring, though i i I would be skeptical because there are so many other factors which make something
Yes,
viral.
absolutely.
But in the long run, right? So let's
Hmm.
say what makes a movie a classic movie is
Hmm.
not really the initial shock value.
Yeah.
So
Understood.
and that's like more in what you showed in the teams example, that initially
Hmm.
there is a learning curve and then eventually
Hmm.
there is a lowering of that
Hmm.
effort, cognitive load, but
Hmm.
it stops at a certain level and remains there, right?
Hmm.
So
Hmm.
so how do you, like, when you propose these kind of things for marketing, how do you balance
Hmm.
between the initial effect versus the long term effect, and also how do you measure the long term effect?
Good question. Good question. So the question is, how sure are we that the neuroscientific basis is the only variable related to the whole ensemble success of a content, say an ad or movie? So in one sense, there's two variables acting here. One is a single person's experience. Second is the social experience. Now, this is where social neuroscience, it is something that is very, very nascent to the point I can't even say it's nascent. But that is probably the answer to all of this stuff. Social neuroscience combines the neuroscience principles as well as network theory, network analysis, like how each person, in this case a node, how the interaction between and information passing between people works out. Now you're saying, yeah, it is initial shock value, but as you can see, after the first in this graph, for example, the first 10 to 20 seconds was a complete prediction error. Like you have no idea what's going to come and all. But the brain, as good as it is, it it learns itself. Like you won't get the same peak again because now it has learned to know that okay, it's not just it's not only that something very violent can happen in the movie, it can happen again and it can happen more and more times. So there's no need to get worried over it. There's no need to have an error on that. But certain errors, when you have an urge to share, right? That is in one sense, in my opinion at least, active inference. Like you get some active inference is if you remember what I said earlier, you actively go and sample the environment yourself. So if you are in part of a community structure, like you had 3 4 friends and you got a massive prediction or massively engaging video content, you would naturally want to share with them. That is, you want to change their active priors and their beliefs by yourself, and sharing is the main way to do that. So the higher the magnitude, I would still stick on to that, higher the magnitude of one person's priors getting violated or the prediction errors, the more chance there is for them to actively infer or share this with the people in their own network community. Now, there are other hierarchies in this network structure as well. Like, what kind of video would you want to share with what kind of people? You obviously don't want to share a very funny video to your extremely professional peers, but only to your friends. So that kind of stuff is always going to be there, and that's where we want to be focusing in the later on when this is all sort as well, like how the population level dynamics owing towards the neuroscience of it evolves. And that is that's probably the main thing that can explain the very viral success of certain movies and how it makes a classic and rewiring in the society itself.
Yeah, thanks. That totally makes sense. And in fact, when you were telling about this shock value, and therefore I go and tell my friend, and that kind of primes my friend, right? And this
Yes.
actually matters a lot, because I have seen sometimes you might oversell, and then when it
Yes.
comes to you go and see with a lot of expectation, even though actually the movie was probably not that bad, because of this overselling you feel, oh, this is
Yes,
not up to my
exactly.
expectation. Yeah.
Exactly. Like certain nodes in the network would have high value among the peers. So if they do something, everyone would want to already would have a certain priors what to expect of the movie. Even if, as you said, the movie isn't that good, just because of the priors, you would have higher value and hence better predictions.
Okay, thank you.
Thank you too.
Any other questions?
All right. I
Yeah.
guess let's thank Fahad for
Yep.
a wonderful talk. I think this talk has been recorded, so
It
if
is.
yeah, I guess Vaishak will share a link to the recording shortly. All right, thanks a lot, guys.